Let's do some math for fun. Today let's talk about the famous Riemann Zeta function. And yes, it's on my shirt already. And even though this right here is considered higher level math, but let me tell you, you just need calculus 2 to understand this video. So check this out. This is what we are going to work with. We are not going to get into a lot of details. We are not going to talk about the analytic continuations. More importantly, we are not going to plug in -1 into the S. Okay? Alright, anyway, zeta of S is defined to be the series as n goes from 1 to infinity of 1 over n to the S power. And this right here should remind you the P series from calculus 2. Well, if we have S being equal to 1 right here, from calculus 2 we know this is actually the harmonic series and it diverges to positive infinity. And then if you take a look at all this, in fact, because all these right here are bigger than 1, they are all convergent series. When we have 2 right here, this is actually a very nice question as well, and the answer for that is pi squared over 6. We have a very nice result. Let's talk about this later. Let's look at when this right here is equal to 4. Okay, it was 1 over n squared earlier, this is 1 over n to the 4th power now. So maybe because we already know the series as n goes from 1 to infinity of 1 over n squared is that, let's just go ahead and square that. Check this out. Pi squared gives us pi to the 4th power, and then 6 squared gives us 90. Okay, I know, just kidding. By the way, this is legit. This is actually the correct answer for that. But of course, you cannot just square this to get that. Don't go yet. I do have a video going over how to come with this result, so go ahead and check that out if you would like. But anyway, I want to tell you guys that though, if we have an even number inside, we actually will end up with a very nice answer involving pi. Pretty cool, huh? But you know what's cooler? When we have an odd number inside. When we have 3. In fact, this right here is a whole new constant on its own. This is called the Paris constant. Unfortunately, it does not have a closed form in terms of pi, e, square root of whatever. None of that. It's just a new constant on its own. Similarly for zeta of 5, etc, etc. And of course, zeta of 1 is infinity, which is really cool as well. Okay, all this right here converge. How about, let's take a look right here. What if S goes to infinity? Then we are looking at the series as n goes from 1 to infinity of 1 over n to the infinity's power. Of course, we are talking about taking a limit, but what do you guys think what the answer right here is? Well, let me tell you, the answer to this right here is nicely equal to 1, right? How? Well, I'm going to do that at the end of the video. Because if you take a look right here, this is pretty cool. We have a series, but you know what? Sometimes it's even better, it's even cooler to put a series inside of another series. This is not my question, right? It was asked by R3TT4. Thank you for your question. Check this out. This is the question of the day. Let's go ahead and put the Riemann Zeta function in a series. So let's go ahead and do this. When S goes from, we cannot put down 1 because when S is 1, we get infinity. So let's go ahead and start with 2 and then to infinity. And then we are looking at the zeta of S. So this is technically a series inside of a series. But you know what? This is too easy because we know if we do the test for divergence, take the limit as S goes to infinity. As I told you earlier, this is going to be 1. If you just sum up lots of 1s, this right here, of course, diverges, which is not fun. But you know what we are going to do? Look at this, and then just go ahead and minus 1 inside. So you see that if you do the test for divergence, take the limit of this, this is actually 0. And you cannot really draw conclusion, right? But let me just tell you that this right here does converge. Alright, first off, we are going to replace this with the series that we saw earlier. So first we have this right here, the series as S goes from 2 to infinity. And for this guy right here, I'm going to put it down in blue and you will see why. This is the series as n goes from 1 to infinity, and we have 1 over n to the s power. and let's put a parentheses to close that, and we have the -1 after that. All right, now check this out. This series starts at 2, but this right here starts at 1. Let's just go ahead and put a 1 right here so we can squeeze out the first term. So let me just write this down again. We have the series as s goes from 2 to infinity, and when we put a 1 in here, 1 over 1 to the s power is just 1. So that will be the first term. And then we picked up the rest, which n will be going from 2 to infinity, and we have 1 over n to the s power. Okay, this is so nice. Because we see we have the -1 after that, right? And we can just do this and that. Cancel. This is just a double summation. And the beauty is that they both go from 2 to infinity. We can switch the order of summation easily. And we want to do that because if you look at this right here in the n world, we cannot do too much. But if you look at this in the s world first, in fact, that's just a geometric series. So let's go ahead and switch the order of summation. We are going to have the blue one on the outside. So the series as n goes from 2 to infinity. And we have this, the series as s goes from 2 to infinity. And for this right here, I'm going to write it down as 1 over n and then raised to the s power. And if you guys would like to have another example of how we can switch the order of summation, I have that for you in the description. But anyway, take a look. You see this right here is a convergent geometric series. Why? Because n is bigger than 2. So this right here converge, right? Cool. So let's go ahead and put this down. I'm going to just write down the blue series on the outside again. So series as n goes from 2 to infinity. This right here converges to the first term, which you just put a 2 in here. So we get 1 over n and then square and then divided by 1 minus the common ratio, which is 1 over n. All right. And we are going to clean this up a little bit. Multiply this by n squared and then multiply this by n squared. Okay, continue from here. This is equal to, again, the blue series on the outside as n goes from 2 to infinity. And we see that this times this is n squared and this times this is minus n. So we can factor out an n, right? And when we do that, I'm actually going to write this down. Let me put down the n minus 1 first and then the n. And on top we just have 1. So that's what we have. And now, do we recognize what kind of series this is? Yes, this is just a telescoping series from Calculus 2. So let's go ahead and figure this out. And again, let's go ahead and write this down. We have the series as n goes from 2 to infinity. Break this down with partial fractions. We know the first little fraction will have n minus 1 for the bottom, and then the other one will be some number over n. Okay, to figure this out, we go back to the original and cover the same denominator. And how can we make n minus 1 0? N has to be 1. Put a 1 in here. 1 over 1 is just 1. This is the cover-up method to figure out the partial fraction. Let's do it again right here. To figure this out, we go back to the original, cover the same denominator, and ask yourself, how can we make n equal 0? N has to be 0. And put a 0 in here. 1 over -1, we get -1. Done. And I will show you guys the quick way to do the telescoping series. First, notice that they are off by 1 term. So you do the following. We are going to be plugging 2. We are going to be plugging 2 into here 1 time. That's all. We are going to be plugging 2 into here, and we just need the first term. That's all. So we get 1 over 2 minus 1. Okay? And then we also need to have 1 term from here, and it's just that, which is just minus 1 over n. And we just have to take the limit as n goes to infinity of that. That's all. As n goes to infinity, this guy goes to 0. And ladies and gentlemen, all in all, we just get 1. I really don't know how to feel about this because it's such a cool question, but in the end, we just end up with 1. But it's really cool. But in the meantime, I was expecting to have some crazy numbers like the ones I showed you guys earlier, but not so much. But anyway, you guys can let me know what you guys think about this. Do you find calculus interesting? If so, then I think you should check out Brilliant, because I believe you will benefit a lot from them. Brilliant is an online learning platform with a big focus on interactive learning. This is from their Calculus in a Nutshell course. This course uses visual and physical intuition to present the major topics of calculus, including limits, derivatives, integrals, and infinite series. You will walk away with a clear sense of what calculus is and what it can do. All of their courses are really fun because they will always keep you engaged by storytelling and beautiful animations. Besides calculus, they also have a lot of other classes for you to choose from, including number theory, discrete math, probabilities, and a lot more. So go ahead and take a look, and if you use the link in the description, brilliant.org/blackpenredpen, then you can receive a 20% off discount. I want to thank Brilliant for sponsoring this video, and I also want to thank you for checking them out. Alright, here's the bonus part. Let's figure this out. Of course, this is the same as. And just like earlier, I'm going to put down the 1 inside here and then squeeze out the first term. If you take a look right here, when you plug in 2, you get 1 over 2. And you see this right here is s goes to infinity. So we have this, right? 1 over 2 to the infinity. And then the next one is just going to be 1 over 3 to the infinity, and so on, so on, so on. Yes, this right here goes to 0, and yes, this right here goes to 0. 0 plus 0 is 0, but the problem is that we have infinitely many zeros. And in fact, this is not exact 0 because this is the limit. This is the limit, right? It's not exact 0. So you cannot really do this. Let's focus on this guy. And we're going to make it bound. This is the classic way to do it. Let's look at a function 1 over x to the s power. And that would look like this. 1 over x to the s power. And of course, in order for this to make sense, s has to be greater than 1. Otherwise, it wouldn't converge at all. And of course, it's greater than 1. That's also clear. But anyway, let's go ahead and just make some mark. 1, 2, 3, 4, and so on. This right here starts at 2. This is how we can produce this series in this picture. You just go to 2, and then you make a rectangle, like so. Because when you put 2 into the x, you get 1 over 2 to the s power. And then again, do the same thing, and so on, so on, so on. So as you can see, if you have that series, which is all the rectangles here, the series n goes from 2 to infinity, 1 over n to the s power. This will be less than or equal to the improper integral going from 1 to infinity of 1 over x to the s power. Why? Because this is just an area argument. And as we said earlier, this right here is greater than or equal to 0. So now let's figure this out. And I'm going to put it down right here. We have the integral going from 1 to infinity, and we have x to the negative s power. Add 1 to the power, we get x, and let's do 1 minus x, like this. And divided by the new power, so we have over 1 minus s. And then plug in. When we put infinity to here, we get infinity to a negative power because s is bigger than 1. So the first term is 0. That's nice. And then when we put 1 right here, it's just 1 over that. So we have this, and then 1 over 1 minus s. Yeah. So that's that. And of course, you can use the negative to switch the order of the subtraction, but doesn't really matter. I'm still going to do it. 1 over s minus 1. And of course, in the end, we just have to take the limit as s goes to infinity. And as we can see, when we have infinity right here, this is just 0. So you can see that this guy is being squeezed in between of 0 and 0. So it must be approaching 0. Therefore, ladies and gentlemen, all in all, yeah, we're doing just a lot of work again for the 1 right here. Yeah, pretty cool. Let me know what you guys think.